Imagine a ball that refuses to move until you push it, or a car that slows down when its brakes are applied. These everyday experiences are governed by three simple rules discovered by Sir Isaac Newton over 3 centuries ago. Motion is the continuous change of an object's position relative to a reference point over time. Without a systematic framework, predicting how objects move would be chaotic and unreliable. Newton's laws provide that framework by linking forces to motion through clear principles. The first law states that an object remains at rest or in uniform straight-line motion unless acted upon by a net external force. This principle explains why a ball on a flat surface stays still until someone pushes it. The second law quantifies the relationship between force, mass, and acceleration with the equation F equals ma. When a car accelerates, the engine applies a forward force that overcomes friction, producing a measurable increase in velocity. The third law tells us that every action has an equal and opposite reaction, which is why rockets launch upward as exhaust gases rush downward. By applying these laws, scientists can calculate trajectories of projectiles, predict planetary orbits, and design efficient transportation systems. Thus, understanding motion through Newton's framework transforms observation into precise prediction across physics and engineering. Pause 0.8. Newtonian Eurostrade's first law states that an object will stay at rest or keep moving uniformly unless something pushes it. In a frictionless world, the only thing that can alter motion is an external force acting on the body. Imagine a crate resting on a smooth table. No forces are pulling or pushing it from any side. Because there is no net force, the Kratia Eurostrade's velocity remains zero and its state of rest persists. Now apply a gentle push to that same crate. The applied force becomes the only external influence. The force creates an unbalanced vector, causing the Kratia Eurostrade's velocity to change from zero toward the direction of the push. This acceleration is directly proportional to the magnitude of the applied force and inversely related to the Kratia Eurostrade's mass. If you stop pushing, the external force disappears. The crate then continues moving at a constant speed. The only way to halt it is to introduce another force that counters its motion, such as friction or a brake. Thus, the first law encapsulates inertia. Objects resist changes in their state of motion unless acted upon. In educational demonstrations, a Cydia Euros by Euros side animation clearly shows the stationary crate beside the moving one after a push. Highlighting the velocity vector and labeling the applied force helps students visualize how an external influence breaks inertia. Pause 0.8. When a car is pushed, the applied force initiates motion by changing its velocity. Newtonian Eurostrade's second law states that the net force equals mass times acceleration, expressed as F equals ma circumflex a. In this diagram, the red arrow labeled F points along the direction of the push and shows magnitude. The blue arrow labeled A indicates how quickly the car Eurostrade's speed changes in that same direction. Because mass is constant for the vehicle, increasing the force directly increases acceleration proportionally. Conversely, if the applied force remains fixed, adding more mass reduces the resulting acceleration. The arrows Eurostrade lengths visually encode these relationships. A longer F arrow yields a longer A arrow when M is unchanged. This proportionality can be tested by measuring time intervals for identical distance increments under different forces. Graphing acceleration versus force produces a straight line, whose slope equals 1/m, confirming the law Eurostrade's prediction. Thus, the mechanism of motion is governed by the balance between applied force and the resisting inertia of mass. Students can verify this by applying different weights and observing the resulting speed changes. Pause 0.8. When a swimmer pushes water backward, the water exerts an equal force forward on the swimmer. This pair of forces is always simultaneous and acts on different bodies. The backward push is the action force applied by the swimmer to the water. The forward push that propels the swimmer is the reaction force from the water. Because the forces are equal in magnitude, the swimmer experiences a net acceleration only if other forces differ. In practice, friction with the pool walls and air resistance slightly reduce the swimmer's speed. The key point is that no single body can feel an unbalanced action without its reaction counterpart. If the swimmer stops pushing, the reaction force disappears and the swimmer slows due to drag. This principle also explains why a rocket expels exhaust gases backward while moving forward. In all cases, the forces are internal to the interacting system, but external to each individual body. Observing these paired arrows in diagrams helps students see that action and reaction always coexist. Understanding this mechanism clarifies many everyday motions, from walking to launching a projectile. Pause 0.8. When a driver presses the brake pedal, The friction between the tires and the asphalt exerts a backward force on the car. According to Newton-Eurostrada's first law, this backward force reduces the car Eurostrade's forward momentum until its velocity becomes zero. The braking system converts kinetic energy into heat through the frictional contact in the brake pads and rotors. In contrast, a rocket launch begins with the combustion of propellant inside the engine chamber, producing high-pressure exhaust gases. Newton-Eurostrade's third law states that as these gases rush out of the nozzle, an equal and opposite thrust pushes the rocket upward. The magnitude of this thrust depends on both the mass flow rate of the expelled gas and its exit velocity relative to the vehicle. While the car relies on external friction forces, the rocket generates its own propulsive force by expelling mass in the opposite direction. Both scenarios illustrate how Newton-Eurostrade's laws predict motion. A backward force slows an object, while an equal forward reaction accelerates it. Engineers design braking systems to maximize friction and minimize stopping distance, whereas rocket designers optimize nozzle shape for maximum thrust efficiency. Understanding these mechanisms allows us to anticipate vehicle behavior in everyday traffic and interplanetary travel alike. Pause 0.8. Many students think that a moving object will keep going forever because of inertia. In reality, inertia is simply the tendency of an object to maintain its state of motion unless acted upon by an external force. The first law states that if no net force acts on an object, its velocity remains constant. It does not imply perpetual motion in a frictionless world. A common misconception is that all surfaces are frictionless, so a block sliding down an incline would accelerate indefinitely. In practice, kinetic friction between the block and the incline provides a resistive force equal to mu k times the normal reaction, which reduces acceleration. The second law quantifies this by relating net force ma circumflexa to mass and acceleration. The frictional force is part of that net force vector. When students ignore friction, they misapply the equation A equals g sin theta, overlooking the term mu kg cos theta that opposes motion. Another misunderstanding involves applying Newton's laws at very high speeds or in strong gravitational fields, where relativistic effects become significant. In such regimes, the simple ma circumflexa relationship is replaced by momentum conservation expressed with relativistic mass and time dilation corrections. Likewise, on microscopic scales, quantum fluctuations mean that classical forces are not well defined, so Newtonian mechanics loses predictive power. Therefore, it is crucial to recognize the domain of validity. Everyday macroscopic scenarios where speeds are much less than light speed and gravitational fields are weak. By acknowledging friction, non-inertial reference frames, and limits of applicability, students can avoid common pitfalls and apply Newton-Eurostrade's laws correctly. Pause 0.8. Newton-Eurostrade's laws provide a clear, mechanism-first framework for predicting how objects move. By understanding inertia, the relationship between force, mass, and acceleration, and action Euros reaction pairs, we can analyze everyday phenomena Euros from a car braking on a road to a rocket launching into space Euros and recognize where classical mechanics applies and where it breaks down.